Since we are already done calculating the equivalent stiffness per floor, let's proceed with our next step. Determination of the stiffness matrix and as well the mass matrix. Our equivalent stiffness for the first floor is 10,903,666.05 Newton per meter. The equivalent stiffness for the second floor is equal to 21,296,222.75 Newton per meter. And then the equivalent stiffness for the third floor is equal to 25,845,726.92 Newton per meter. And then our mass 1 is equal to 5,000 kilograms. Our mass 2 is equal to 2,500 kilograms. And then our mass 3 is equal to 1,250 kilograms. Okay, let's write our stiffness matrix. Now, in the stiffness matrix, we have a pattern. Remember, we have K1 plus K2, negative K2, negative K2, and K2. This is for the 2DOF system that we have previously calculated. Now, what will happen for a 3DOF, 4DOF, so on and so forth? The pattern will become, we have here, the diagonals will have this one. So, we have the negative K2 and then also the negative K2. And then here we have the negative K3 and then the negative K3 and then the K3. This is for the 3DOF system, which is similar to our example. Now, what will happen if the example or the problem is for the fourth story, fifth story, so on and so forth? Then we'll just have this pattern that the diagonal are just the summation of two consecutive stiffness. And we have the K2 plus K3, and then we have the K3 plus K4, and we have the K4 plus K5, so on and so forth. And then the rest there, besides and above the diagonal, we have the negative of the succeeding stiffness, and then we have the negative K3 here and the negative K3. We have the negative K4 and negative K4, so on and so forth until the final stiffness. We'll have also the negative Kn there and negative Kn. Then how about the rest? The rest is just 0. So on and so forth. So this is just the pattern for the stiffness matrix. How about for the mass matrix? For the mass matrix, it was pretty obvious that diagonal are our masses, so on and so forth. And then the rest are just 0. So on and so forth. Let's rewrite that one. Our stiffness matrix for this problem, since this is a 3DOF system, we have the K1 plus K2, negative K2, negative K2. We have the K2 plus K3, negative K3, negative K3, and the positive K3. And the rest is equal to 0. Now, if we add K1 and K2, we'll arrive with 32,199,888.8 Newton per meter. And then our K2 is equal to negative 21,296,222.75. We'll arrive with this one for our stiffness matrix. For our mass matrix, we just follow the pattern that the diagonals will be the masses and the rest are just 0. We'll have this as our mass matrix. Now you need to take note that even though these are matrices, we can factor out their common factor among uh, the given values. Now for this one, would like to factor out something from the mass matrix. So why we're going to factor out this one? It is because if you're going to look again at our stiffness matrix, there are already in millions. Now, if you multiply these millions times the 5,000 or 2,500 and 1,150, the value will become much larger. Now, much more if you're going to multiply millions with millions. So for the mass matrix, I'd like to factor out that this is up to you if you're going to factor out the 1 to 50, the 2, 5, or the 5,000. But for me, let's say for this example, I'd like to factor out the 5,000. So 5,000 divided by 5,000, are left with 1, and then the rest is 0. And we have the 0, and then we have the 2,500 divided by 5,000 is 0.5. We have 0, and 0, 0, and 1 to 50 divided by 5,000 will have 0.25. Okay, this will be our mass matrix. Next step, now we'd like to make it in this form. Stiffness matrix minus omega squared times the mass matrix. Dali rin siya. The mass matrix minus omega squared times, sorry, the stiffness matrix minus omega squared minus omega squared times the mass matrix. So for this stiffness matrix, let me rewrite it just first as the stiffness matrix minus omega squared. We have the times 5,000. If you remember, no, from this one, we have the 5,000 and then the matrix. And then we have this 100, 0.50, 0.25. Now, if you'd like to ask why I'd just write the stiffness matrix as this first, it is because we need to resolve this part first. So does that we're not going to write uh, so much in the in our calculations. Now, if you notice, we have omega squared on that part. Actually, we can rewrite that one. We can let p as our omega squared, or we can just have omega squared as is in the matrix, or we can write that p is equal to omega squared. Why? So that it will be not so bothersome for several students or persons. Now, what if, let's say, there is another value there. For example, that is 2.5 omega squared, so on and so forth. You can also write 2.5 omega squared as equal to b whatsoever. It depends on the value there. Now, again, let me rewrite the stiffness matrix. We have this or stiffness matrix, and then we have the minus 5,000 omega squared as the mass matrix 100, 0.50, and then 0.25. Now, there is a 5,000 there. We can divide that 5,000 to the whole equation. So, you divide the 5,000 on this part and as well on this side. So, everything here will also and can be divided by the 5,000. So if we divide the 5,000 to the whole equation, we will arrive that our stiffness matrix will become this one, and then minus, so since our omega squared, no, we let b is equal to omega squared, and we can rewrite that as b times 100 as the mass matrix rather. So this is much better because if you look closely for with on the stiffness matrix part, the values there are already in thousands instead of billions. So next, what we're going to do next, we're going, if we can factor out, from the items here, we can also distribute this b from the items here. So we have b times 1, so we'll have b times 0 is the 0, so on and so forth. We can distribute this b here to everything there. We have our stiffness matrix minus, and then we distribute the b. We'll have b 0, 0, 0, 0.5 b 0, and then 0, 0, 0.25. What is the next step? We have already factored out, divided the 5,000 to the whole the equation, and then we have already let b as our omega squared, and then we have distributed b back to the mass matrix. Next is that we're going now to apply the operation that is present there in order for us to form a single matrix. So how are we going to do this? We're going to apply the subtraction operation there. So that is just this row and column specific point minus this part there, and then this one minus this part here, and then this one minus this part here, and then this middle row first column minus here, so on and so forth. Then actually we will arrive with the single matrix equal to, so we have this form. We have already our single matrix now. This matrix here, that is our stiffness matrix minus omega squared times the mass matrix. We have already arrived in this formation. Next step is we're going to get the determinant of that simplified matrix. And getting the determinant, you can use the Kramer's rule, or you can just apply or use the basket method. So for this one, for the three DOF or 3 degree of freedom system, we can use the basket method in getting the determinant of the matrix. So we have the determinant of the stiffness matrix minus omega squared times the mass matrix. We have, so by applying the basket method, you're going to write the matrix doubly. So what will happen with the matrix basket method is that you multiply those in the diagonal. So you multiply these things here inside here. So and then plus the product of this diagonal plus the product of this diagonal, and then minus what? Minus the product of this diagonal minus the product of this diagonal minus the product of this diagonal. So okay, so let's start our calculations. We have our first diagonal here, that is quantity 6,439.978 minus b times, this is our first diagonal, plus the second diagonal. Now if you look closely with the second diagonal, we have a 0 on this part. Now, any number multiplied to 0 is 0. So we have plus 0 plus the product of the third diagonal. Now, on the third diagonal, we have also a 0. So any number multiplied with 0 is just equal to 0. Next is minus these diagonals in the yellow ink, orange ink rather. So we have there minus 6,439.978 minus b times negative 5,169.145 times quantity negative 5,169.145, and then minus the second diagonal, we have negative 4,259.245 times quantity negative 4,259.245 times 5,169.145 minus 0.25 b, and then minus on the third diagonal here, we have a 0. So any number multiplied to 0 is just equal to 0. Next is, you just distribute the values here, so on and so forth, and then eventually, uh, by distributing those values, you will arrive with a cubic equation. So take note for this, if the degree of freedom system is 3, or the building is a 3-story, then therefore we'll have a cubic equation. If the building is 2-story, then we have a quadratic equation. If the building is 4-story, then we'll have an equation that is raised to the fourth power, so on and so forth. So we have an we'll form a cubic equation that is equal to, we have the negative 0.125 b cubed. So actually, if you continue the calculation, you will arrive with this one. Negative 0.125 b cubed plus 5,746, 5,746 and 0.66725 b squared minus the 80,560,961.12 b plus 313 billion 863,372,600 is equal to 0. Now, how are you going to solve the cubic equation? For the cubic equation, you can use your scientific calculators, and then you'll arrive with 3 roots. So for quadratic equation, you'll have 2 roots. For the cubic equation, you'll have 3 roots. We will have b1, b2, and b3. That is very important that you are going to write the roots in ascending order, with b1 as the lowest root. Why? We are going to make b1 as our, what we call, the fundamental frequency. Here, what is the fundamental frequency? The fundamental frequency is the frequency with that is the lowest frequency among others. So actually, aside from that, the lowest frequency in the given MDOF system will actually yield a single direction, the mode shape of all the floors are on the same direction. Later on, I'm going to show you what is the sketch, or how this the fundamental frequency looks like. So we'll have 3 roots. It is very important to write your B1 as your least, or the lowest one. So our first root, or the lowest root, or the fundamental frequency, is equal to 1,115.212, and then the second root is 9,833.655, and then the third root, the highest, is 35,024.471. Okay, from here, if you remember, our b is equal to omega squared. Now to get the natural frequency, we just extract 2 square root the b. So for our first frequency, that is just the square root of b1. And then that is equal to 33.395 radians per second. Our second natural frequency, that is equal to 99.165 radians per seconds. And our third natural frequency is equal to 187.148 radians per seconds. We have already our natural frequencies. Next is we're going to calculate the period or the time. If you remember, the period is equal to 2 pi over the natural frequency. Our first period, that is 2 pi over omega 1, and that is equal to 0.188 seconds. The second period, that is just equal to 2 pi over omega 2, that is equal to 0.063 seconds. And then third period is equal to, we have the 2 pi over omega 3, that is equal to 0.074 seconds. Is you're already done with the calculation of the stiffness, the natural frequencies, and the period. In the next discussion, we'll start calculating the values for our mode shapes.